Monday, January 11th, 2021, AP Physics C Mechanics. We're doing example 8.6 out of our textbook with the values modified. It goes like this. I have a car. The car has a mass of 1,200 kilograms. It is starting from rest, and it is going to go around and around on a circular track that has a radius of 36.0 meters. A constant accelerating force of 500 newtons is being applied in the forward direction at all times. The coefficient of static friction between the tires and the flat road is 0.900. The question is, how many revolutions will the car complete before it slides out of the curve? From my point of view, the first step would be to calculate the acceleration of the car. And I would do that using Newton's second law, F equals ma. In this case, it's going to be the centripetal acceleration that I am calculating. Actually, that's not true. The tangential acceleration, I'm sorry. Well, if F equals ma, then A equals F divided by m. So if I calculate 500 newtons divided by 1,200 kilograms, then 5/12 will be my acceleration. And we're going to do this to 3 sig figs. I get 0.417 meters per second squared as the acceleration tangentially of this car, beginning from rest. Tangentially, I can treat the car as if it were going in a straight line and use any of the 4 kinematic equations, such as final velocity equals initial velocity plus acceleration times time. And all 4 of them are applicable because this is a constant acceleration. The fact that the direction is changing constantly doesn't invalidate the kinematic equations as far as the tangential acceleration goes and the tangential speed is concerned. So that's good to know. Now, a fair question would be to ask, for what speed would the car slide? When it's at rest, it's not going to slide. As it speeds up faster and faster and faster, the centripetal force necessary to keep it pointed towards the center of the circle is increasing. At some point, the car will be going so fast that there will not be a sufficient static force applying the necessary centripetal force to keep it in a circle. The amount of static frictional force available is equal to mu times the normal force. Well, the normal force is the weight of the car. So mu mg would be the maximum force of friction that we could have in this situation. But I'm going to make the bold claim that the mass of the car is going to cancel out, that it's not really necessary to even have a designated mass for the car. Indeed, if I take the force and call this the radial force, and think of that as the mass times the radial acceleration, then I can cancel the mass over here and say, oh, the radial acceleration is limited to the coefficient of static friction times the acceleration due to gravity. And that would be 0.9 times g. Our textbook seems to be using a value of 8.91 meters per second squared. So if I use that value, I have 8.83 meters per second squared as the maximum radial acceleration sustainable by this car before it begins to slide. Well, radial acceleration is v squared divided by r. Actually, I see I'm overlooking a factor here. I'm thinking that I've done everything correctly so far. This is how we calculate yeah, so I've made a mistake. I'm sorry, I've made a mistake. My mistake is that there is a radial acceleration, which draws an arrow pointing to the left for this moment on the circle. But in addition, there actually is still a tangential acceleration in the forward direction, which at this moment, we even know its value is 0.417 meters per second squared. And that's going to be a constant no matter how fast the car is moving. The radial acceleration is a function of the square of the speed of the car at any moment. So this will increase from zero, increase, increase, increase. The car will begin to slide when the total acceleration is exceeding 8.83 meters per second squared, not just the radial acceleration. So I need to kind of correct for that. The total acceleration is 8.83 meters per second squared, or else the car will begin to slide. The tangential component of that is 0.417 meters per second squared. So now I can solve what is the correct radial acceleration. It's going to be, so this is a mistake here. This should be total. I'll put a T for, well, I'll write the word total. There you go, bad handwriting. I'm going to use Pythagorean's theorem and ask it, what is the square root of 8.8? And I know this was actually 8.829. I think I will go ahead and put that back in to 4 sig figs. 8.829 squared minus 0.41, and I'll do that to 4 sig figs too. 0.4167 squared. Enter. And it says, aha, the radial acceleration really can't exceed 8.82 meters per second squared. You could say that's almost not worth mentioning, but I want to mention it. So there you have it. If the tangential acceleration were greater in magnitude, then this difference would be greater as well. Okay. So it's only because we randomly had a small force being applied that the difference is relatively small. But it is there. And so now we have the correct value for the radial acceleration to solve for in this problem. The radial acceleration is v squared divided by r. I can now solve for the tangential speed at which the radial acceleration will be 8.82 meters per second squared. In fact, if I take the square root of 36 meters times 8.8, oh, I'm tempted to call it 8.819 because that's what it said on the calculator. Sure, to 4 sig figs, meters per second squared. The speed at which the car will begin to slide off the track is the square root of 36 times the answer on my calculator. Oops, still getting used to a TI-84 plus color edition. And it says 17.8 meters per second. This will be the speed at which the car begins to slide off the track. Now we go calculate how much angle will we turn through on our way to that speed? I mentioned earlier that the kinematic equations of motion apply. Here's equation 1. I could solve for how much time it takes to get to there. But I don't even need the time. I really want the angle. And so I would use the fourth kinematic equation of motion that says the final velocity in the tangential direction, by the way, squared, is equal to the initial velocity in the tangential direction squared, plus 2 times the tangential acceleration times the distance that it travels. And by the way, displacement would be 0 every time it completes a loop, so it would have to be distance here. Now, this is the linear version. Of course, the angular version, I still think I'm doing this correctly, but this will be the distance, I'll call it d, that it travels around the track. When I solve for d, I'm going to be doing 17.8 squared, 17.8 meters per second squared, divided by 2, divided by 0.417 meters per second squared. And what do I get when I do that? 17.8 squared divided by 2 divided by 0.417 is 380 meters. And that's equal to 2 pi r. So if I were to then divide this by 2 and divide that by pi, I'm sorry, and then divide that by r, there we go. So if I divide this by 36 now, I get 1.68 revolutions as my answer. It does make me wonder if I did it correctly. We're going to take a look at example 8.7, which is a challenge problem. We have a shaft, and the shaft is rotating very fast. There's a ball, and this upper string is 1 meter long, this lower string is 1 meter long, and the distance from the top to the bottom connection points is also 1 meter. What they want is the minimum speed and revolution per minute at which the ball would be as shown here, forming this equilateral triangle. And what they're pointing out is that this would be right at the speed at which the tension along this lower string would be 0. So really, it is a conical pendulum problem where you have a pendulum swinging around in a cone, that the cone forms a right triangle as you sketch it. The hypotenuse is 1 meter. The vertical leg is half a meter. When you do the free body diagram of this ball, there will be the force of gravity acting vertically downwards. They do give us the mass of the ball, which I claim should cancel out, but they say it's 250 grams. Maybe it doesn't cancel. Interesting. Then there's the tension in the string, which is pulling up and to the center of the circle. And this is badly not to scale because the vertical component of the tension has to be equal to the weight downwards. So the vertical component of the tension has to be equal to 250 grams times 9.81. I get 2.45 newtons is the upward component of the tension. The angle by geometry is established here. This angle is the inverse cosine of 1/2. The inverse cosine of 1/2 is 60 degrees. What am I after? I'm after the radial component of the tension. And really, this is a 60 degree, 30 degree, 90 degree right triangle where the vertical leg is 2.45 newtons. And I want the horizontal component, the x component of the tension or the applied force. And that one is related to the opposite leg. Let's see, this is 2, 1, radical 3. I could say it's square root of 3 times greater than 2.45. There we go. So if I multiply this by the square root of 3, then the horizontal component of the tension is 4.25 newtons. If I divide that by the mass of 250 grams, then I have a radial acceleration of 17.0 meters per second squared inwards. We have our 3 minute. All right, 3 minutes have gone by, and it's time to just finish up this problem. The radial acceleration that satisfies these conditions is a value of 17.0 meters per second squared. Now, we can turn that into V equals R omega. Centripetal acceleration, radial acceleration, is equal to V squared over R, or R omega squared. We're more interested in this form this time around. We'd like to solve for omega. Omega is the angular speed in radians per second. And once we have it in radians per second, we can turn it into revolutions per minute and be done with this problem. For the moment, we have 17.0 meters per second squared is equal to R omega squared. What is the value of R? We get that by geometry. This is a 30, 60, 90 right triangle where the hypotenuse is a value of 1. This vertical leg is a value of 1/2. And this radial distance from the axis of rotation, that value of R that we need, would be the square root of 3 divided by 2. So the square root of 3 divided by 2 is, I should have known that one, 0.866. Yeah, should have known that one. 0.866. Now we can plug that in here and solve for omega. Omega is the square root of 0.866 times 17.0, which would be the square root of second answer times 17, enter, and I get omega equals 3.84 radians per second. And at radians per second, now, how do we turn radians per second into revolutions per minute? And the answer is, well, one revolution is equal to 2 pi radians, and 1 minute is 60 seconds. So if we have 1 radian per second as an example, then that would be 2 pi radians per minute. Why does that sound wrong? If I was doing 1 radian per second, I should be doing 60 radians per second. And I'm pretty sure I just said something wrong. To convert from radians per second to revolutions per minute, you divide the radians by, well, I would first multiply everything by 60. So I have it radians per minute. And then I would divide that number of radians by 2 pi to convert it to revolutions per minute. So multiply by 60. Haha, yeah, seconds per minute. And then divide by 2 pi. Okay, multiply by 60 divided by 2 pi. 3.84 times 60 is 230 radians per minute. Divide that by 2, divide that by pi, and I have the rate is 36.6 revolutions per minute. And how does that compare with our publisher's answer key? And I have the wrong answer. Our publisher got an answer of 42 RPM. Which is sad. All right, my students pointed out my mistake. Thank you, students. They said, look, I multiplied the acceleration by the radius when I should have divided the acceleration by the radius, which means all the rest of the work after that is wrong. So let's back up to the last place where it was correct. 17.0 meters per second squared was equal to r omega squared. The radius was accepted to be 0.866 meters. So instead of multiplying, how about if I go 17 divided by 0.866? And sure enough, that gives me omega squared is equal to 19.63 radians squared per second squared. Taking the square root of that, it yields omega is 4.43 radians per second, which means I'm now back following our publisher's solution manual. 4.43 radians per second. When I multiply that by 60 seconds per minute, that tells me I have 265.8 radians per minute. 266 radians per minute. A revolution is equal to 2 pi radians. So if I multiply this by 1 revolution for every 2 pi radians, in other words, divide this thing by 2, divide this thing by pi, beep, 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 beep. At last, I've gotten to the answer key. 42.3 revolutions per minute. Thanks to my students. All right, for student selection, we're going to do problem 51 from the end of chapter 8. I have an amusement park ride with a 16-meter diameter. It's rotating once every 4.5 seconds. That's the period. I have a rider's mass of 55 kilograms. And how much force does the ring exert on the rider at the top of the ride? So I'm going to first convert the period of 4.5 seconds into some other useful information. Radial acceleration is equal to v squared divided by r. Assuming that this is constant speed, then the distance traveled in one revolution, 2 pi r, divided by the time, capital T, the period that it takes to complete that revolution, is equal to the tangential speed v. Or in other words, v equals 2 pi r divided by t, the period. So that means I can rearrange a sub r equals v squared over r, and instead write that as 4 pi squared r divided by t, the period, squared. Radial acceleration is 4 pi squared r divided by t squared. T in this problem is 4.5 seconds. R is half of 16 meters because it's the diameter, not the radius, that is 16 meters. I'm going to solve for the radial acceleration. I get a radial acceleration value of 15.6 meters per second squared. That is the total acceleration needed at the top of this ring to accelerate the passengers towards the center of the ring. Now, of that, 9.81 meters per second squared is the acceleration due to gravity assisting in that downward pull. So I'm going to remove 9.81 meters per second squared from that to get 5.79 meters per second squared as the amount of acceleration that has to be exerted on each rider at the top of the ring to force them to continue going in a circle. The centripetal force, oh boy, I'm sorry, the normal force will be the mass of the rider, 55 kilograms, times this residual acceleration that we need. So I get a normal force of 318 newtons at the top of the ride. At the bottom of the ride, we need a centripetal acceleration of 15.6 meters per second squared. But we have to overcome gravity. Gravity's not helping anymore. Gravity's fighting against us. So instead of subtracting gravity the way we had done before, we're going to have to add gravity. 15.6 plus 9.81 means we need a upward normal force that will provide 25.4 meters per second squared of centripetal acceleration. When I multiply that by the mass of this rider, 25 kilograms, I get a normal force of 1,000, call it 400 newtons at the bottom of the ride. Imagine that is a badly written comma, 1,400, and really to 3 sig figs, it's 1397.55 or so, 1,400. There is my answer to part A. Part B, so what is the longest period of rotation that will prevent the riders from falling off the top? Like that person up there, ooh, plop. The longest period of rotation will be when the radial acceleration is exactly equal to the acceleration due to gravity on the surface of planet Earth. So we're solving for a situation where the radial acceleration is equal to 9.81 meters per second squared, and that is set equal to 4 pi squared r divided by t squared. And now you rearrange that equation and solve for t, the period. So 4 pi squared times 8 divided by 9.81. Enter, take the square root of that result, and I get a period of 5.67 seconds. That is the longest amount of time that the Roundup ring can take per revolution without losing passengers. Those are my answers. Okay, students have confirmed that I finally got the right answers to problem number 51, the amusement park ride. We're now going to turn to close out the period, tackling problem 47. A conical pendulum is formed by attaching a ball of mass m to a string of length L, then allowing the ball to move in a horizontal circle of radius r. Figure 8.47 shows that the string traces out the surface of a cone, hence the name conical pendulum. Part A, find an expression for the tension T in the string. Part B, find an expression for the ball's angular speed omega. Part C, what are the tension and angular speed in RPM for a 500-gram ball swinging in a 20 centimeter radius circle at the end of a 1.0 meter long string? Okay, kids, solve. Without looking up the answer key until we're done. So I suppose you probably want me to talk you through the solution while you leap ahead of me doing it. And in this conical pendulum, if you do a free body diagram, you have the force of gravity acting down towards the center of the Earth equal to the weight of the object. You have the tension in the string pulling it radially inward and lifting it upwards vertically. Of course, the tension must always have a vertical component equal to the weight of the object under all conditions. The horizontal component of the tension, T sub x, I'll call it, is the centripetal force to cause this thing to keep going around and around and around in a circle of radius r. Under these, so the free body diagram is telling us the story here, right? The net force is the horizontal component of the tension in the string. The numbers that they gave us in this problem is, first of all, part A, find an expression for the tension in the string. One of the characteristics of a conical pendulum is we tend to express the angle that the string makes with the vertical. So as we create a right triangle for this problem, theta is the angle of the string relative to the vertical. Should be here as well. So if you want to contemplate a right triangle whose vertical leg is mg, whose angle with the vertical is theta, vertical leg is mg, right triangle, angle with the vertical is theta, how would you express the tension? Well, this is the adjacent side of a right triangle, so you could say that the cosine of theta is equal to the weight of the mass divided by the tension in the string. And by the way, I really should caution you, capital T is tension, but in the previous problem, capital T was the period of revolution. They're both capital T. So you have to tell by context which variable we are referring to. In problem 47, capital T is currently the tension. We're down to about a minute of class time. You can say by geometry that the inverse sine of R over L is equal to theta. I suggest we don't have time to actually solve this problem. I'm going to